2, the fundamental theorem of calculus. So, integrals can be found using that ugly definition of integrals, the limits, as we saw in 11.1, that ugly sigma notation limit. However, as you saw, this can be a long and tedious process and not very fun. We also know from chapter 10 that the definite integral of a function from a to b dx represents the area under the curve of a function y equals f of x from a to b. And from section 10.1, we know that this area is equal to f of b minus f of a, where big F is the antiderivative of little f. This follows then that the fundamental theorem of calculus, so just new words, comes if little f is a continuous function on the closed interval from a to b. Then we know if we integrate that function in terms of x over the closed interval a to b, then it is equal to big F of b minus f of a, where big F is any antiderivative of little f. Okay, so just new words. We've done this already. Other notation, we saw this in chapter 9. Okay, f of b minus f of a could be just written as f of x with a square bracket from a to b or a vertical line. And so here's the conclusion. Okay, here is what we are going to be working with today and have already seen. Okay, if I take the antiderivative of little f, then I get big F, and then I'm evaluating it on a closed interval. So what happens to check your answer? Big F's derivative should be little f, okay? All right, let's give this a go. This should look very, very familiar. Evaluate the definite integral of x squared dx on the interval from -2 to 1. Okay, so how do we take the antiderivative of a polynomial function? We add 1 to the exponent and divide by that new exponent. And if we were asked to do the definite integral, we would add c. But we're not asked, so we don't need that. The c's would just cancel, so it doesn't matter what they are. So we're just going to evaluate from our interval -2 to 1. And then we put in the b value first. So it's f of b minus f of a. So I'm going to have 1/5 multiplied by 1 to the power of 5 is equal to, sorry, not equal to, minus 1/5 times -2 to the power of 5. And what does this equal? So I'm going to have 1/5. A -5 times -2 to the 5th is 32. It would be -32 because of the odd exponent. So this is going to become a plus 32 on 5, which is equal to 33 on 5. And there's my answer. Whoopsies, I wanted a different color. There we go. Okay, example number 2. What is the antiderivative of cos? So you really have to think back, if you know your derivative rules, which trig function has the derivative cos, and then work backwards, and the answer is sine. If you don't know that, you certainly can just use your formula sheet or the chart that we are about to look at. So this is being evaluated from pi on 2 to 3 pi on 2. So I'll put that in, sine 3 pi on 2 plus sine, subtract. I'm having problems this morning. Subtract sine pi on 2. And then I'm going to think about my unit circle. Okay, so I have pi on 2, and the coordinates of pi at 2 are 0 and 1. And the coordinates at 3 pi on 2 are 0 and -1. And we want the y values. And so this would be equal to -1 minus 1, which is -2. And in chapter 9, we made a big chart of all of our indefinite integrals in one of the lessons. So here is our table of indefinite integrals that we need to know for this year. I've boxed out all the ones that are from chapter 8 So you don't need to know those for what we are doing. So this first one is a logarithm rule, natural logarithm rule, and that's from chapter 8. The e to the power of x and a to the power of x, that's exponential. So that's chapter 8 as well. And then there's a couple other funky ones there that were never used in our Math 31. So there are 3 from chapter 8 that typically we would cover, and you may want to look at them for interest sake for if you are going to be taking first year calc in university. And then I'm guessing you'll learn those last 2 at university as well. But for us, we don't need to know them for this year. Okay, so just remember, an indefinite integral has no upper or lower limits and is written as the integral of f of x dx and will result in a function. In fact, it is a family of functions because we have to include the extra constant, right? Plus c. Now, what we're really working on in 11.2 is definite integrals. They're going to have upper and lower limits, and it will result in a number. Okay, so a definite integral is going to give me a numeric answer, which we just saw in examples 1 and 2. Okay, a couple more properties that we learned in 9.1 that would be good to remember is if you have a constant in front of your function, you can move it in front of the integral, take the antiderivative of your function, and then multiply the constant through. If you are adding and subtracting 2 functions, you can take those as separate integrals and then tidy up your answer. A couple more properties of definite integrals that we didn't look at in chapter 9 that are useful is the first one. If your boundaries happen to be the same number, then your answer is just going to come out to be 0. Hopefully that makes sense. You're not going anywhere. F of c minus f of c would give me 0. In this second property, if you have boundaries from a to b and you put in a third boundary somewhere in between there, it doesn't have to be in the middle. It can be, anywhere in there, that then you can add those as separate integrals. So you can go from a to c, that would be this piece, and then you could add the integral from c to b. That would be this piece, which is what we did in some of our area questions where our graphs intersected and then we had to make new boundaries in between our extreme boundary from a to b. And then lastly, we have seen this one. It's a little funky one, that if I'm going from B to A, it's the same as going from A to B. See that those switch. And we just need to multiply by -1. Same answer. Okay, so example 3 comes from chapter 8. It's an exponential question. And I'll do this one at the end of the lesson for those people who are interested. Okay, and then the example 4 is similar. It also has a logarithm rule that we would have to use in our antiderivative. So I will look at this one at the end of the video in case anyone is interested. I've put in a couple of new examples. These are not in the lesson package that you would have printed off, just to give you a couple more examples. So this one says to determine the general antiderivative. So this is what we would call an indefinite integral because there's no boundaries, okay? And so we just go about and take our antiderivative as normal. The antiderivative of 6x squared is, well, you add 1 to your exponent and divide by the new exponent, plus the antiderivative of cosecant squared. Well, you're going to need to go to your chart, and that is negative cotan x plus c. Okay, because it is a general antiderivative, meaning take the indefinite integral, we have to remember to add the constant. And then we would just tidy up our answer. So we would get 2x cubed minus cotan x plus c. So our indefinite integral is giving us, change color. Our indefinite integral is giving us a family of functions. And yes, that's not the right way to spell functions. I know, it's my shorthand. Hopefully you can live with it. All right, now this one is what we call a definite integral because we have boundaries. And it's This particular one's going from 4 to 9. Okay, so how am I going to evaluate this? In its given form, I don't have any antiderivative rules that I know how to deal with a numerator and a denominator. So I'm going to have to do some work with it before I can even go about taking the antiderivative. So until I take the antiderivative, I need to keep my integration symbol, okay? Don't drop that. It's like, don't drop the limit symbol, okay? So what I'm going to do is I'm going to give each of these their own denominator of x squared to start with. And the root of x I'm going to write as x to the half over x squared minus 2 over x squared dx. And then I could actually tidy that up. So x squared on x squared is 1 plus x to the half on x squared. So 1/2 minus 2. So what's 1/2 minus 4 on 2? That would be -3/2 minus 2x to the -2, bringing the exponent up in terms of x. Notice how I put brackets around that before I put my dx. Okay, that's just a command to say I'm going to integrate in terms of x. So here I go to integrate. So the antiderivative of 1 is x plus the antiderivative of x to the -3/2. I'm going to add 1. So that's -1/2. So divide by that new exponent minus 2 times x to the -2, add 1. So that's -1. And then I don't, I missed, no, I got one more. Sorry. Minus 2x to the -2 plus 1. So that's -1. And then I don't need to write the plus c. All right. I got them all, I think. And then what does this look like? So before I put in my numbers, let's tidy this up. Okay, so anything divided by -1/2 is going to be -2. So I've got x minus 2x to the -1/2. -2 divided by -1. Oh yeah, I totally did that twice. Man, I'm sorry, guys. Silly me. There we go. Plus 2x to the -1. I need more coffee. All right, here we go. Let's evaluate this before my time runs out on the video. You guys are all shaking your heads. Okay, so we've got 9 minus 2. X to the -1/2 is the root of x on the bottom. So I'm going to write that as root 9 on the bottom plus 2 on x to the -1. So plus 2 on 9. And then subtract, x is 4 minus 2 on square root 4 plus 2 on 4. And then it's just a matter of figuring out what this number is. Put it into your calculator very carefully. You can certainly do some mental math on this if you wish. It's not that hard. It's just a fraction question. The answer should come out to be 91 on 18. Hopefully I didn't make any mathematical errors on that part. Okay, so silly me had done that antiderivative twice. I don't know. Silly. Okay, we're going to come back in video number 2, and I'm going to work with that extra property that we learned with if you put in some boundaries in the middle, so the A to B with the C in the middle. And it's a really good property to see just how things can work. I know it says curriculum extension, but I would like you guys to be aware of this rule. So come back and watch video number 2. And there should be time in that video for me to also go back and look at those chapter 8 questions for example 3 and 4.